Hello, everybody. Welcome back to Calculus 3 online at Frederick Community College. In this video, I will be discussing partial derivatives and how to compute them. And then in the follow-up video, we will also discuss linear approximations of surfaces by tangent planes. So before we jump into the main topic of today's class, let's review a little bit of what we've done in Calculus 1 so you can see the connection between the topics that we've discussed previously now with the material in 3 space. So let's say we have this function f of x, and you can see the graph of this function, okay, in green. Then we can compute the derivative of this function, and we call it f prime of x. And it tells us something about the behavior of the function. It tells us a couple of different things. So over here, for example, at this point, we have a horizontal tangent, okay, and there is a couple more places where that happens, and we know that this corresponds to the fact that f prime is equal to 0 at these points, right? Okay, so f prime is 0 for this particular picture at 4 points. Okay, then what else can we say? Well, if we just evaluate the derivative at some fixed number, okay, some fixed value of x, it tells us the instantaneous rate of change of the function at that point, or the slope of the tangent line. Okay, so for this particular point that I picked, we can say the derivative is negative. Okay, we can see the tangent line going down to the right. Okay, and let's say we have another point right here, point B. So for this particular point, the derivative is positive, and you can see that those points where the derivative is negative, that's where the function is changing behavior from increasing to decreasing, and then from decreasing to increasing, okay, depending on which function that you're working with. But you can see that as we go along the x-axis, okay, so we move in this direction right here, okay, the function does various things, so it's increasing and then decreasing, and we can compute the derivative of the function that will give us the rate of change of f, or y in this case, right? So y is the dependent variable, as x goes from negative direction to positive direction. Okay, so that's just a quick reminder of what we've done and what we've discussed in Calculus 1. Now that we are in Calculus 3, we're working with functions of 2 or 3 variables, right? Okay, so our graph is no longer a line. The graph that we will be working with is a surface, right? So here is some surface in 3 space. We have a point with coordinates x null, y null, z null. And let's say the surface is defined by an explicit equation, z is equal to some function. And now we have 2 independent variables. Okay, so in our previous examples, we had 1 independent variable, x. Okay, so now we can compute, we should be able to compute partial derivatives with respect to the 2 independent variables, x and y. Before we do this, let's discuss what does it actually mean. Okay, so I am on the surface at some point P, and I would like to know how my function changes if I move in a certain direction. But now, as you can see, there are many different directions we can go. Okay, for example, we can go in the direction of the x-axis. Okay, so if we go in this way, okay, along the line that represents the x-axis, we can see how the function is changing. Okay, or what if we go in the direction of y? Okay, so our partial derivatives will tell us how the function is changing if one of the variables is fixed. Okay, so let me go ahead and introduce the notation for partial derivatives. So the common notation that we're going to be using is z sub x. This is the partial derivative of this function with respect to x, and it tells us the rate of change if I fix, okay, so y is fixed, okay, and if I fix my y, treat it as a constant, and then I compute the derivative with respect to x, that will give me the instantaneous rate of change at a point, if we evaluate it at a point, if we are moving in just x direction. Okay, now what about the other direction? Well, the notation for that would be z sub y. Okay, so let me make a note here. This is y is fixed. This is x is fixed. And what does it mean? You just treat it as a constant. Okay, so z sub y will give me the instantaneous rate of change. If I fix my x, right, so x will be fixed and I'm going in the y direction. All right. Okay, so that's the intuitive definition of the derivatives, and how to compute them will become a lot more obvious once we do computations. Okay, now of course the textbook goes through like a whole rigorous explanation of what partial derivatives are in terms of limits. You don't need to worry about that rigorous definition. If you're interested in reviewing, go ahead and do that. But for our class, we're really just focused on the computational aspect, okay? As long as you understand how to compute partial derivatives and then when to compute them, depending on the problem, then you should be good, okay? So let's go ahead and compute some. Okay, so there is a whole bunch of examples that I will go through. Okay, so this problem right here says compute the first partial derivatives of the given function. Let me also go ahead and introduce an alternative notation. So besides f sub x and f sub y, you will also see the operator notation. So dy, that's the partial with respect to y. And then dx, that's the partial with respect to x. Okay. Let me go ahead and put that f there. All right. So that's what the notation, that's the most common notation to use. I prefer to use this one. Okay. And you can choose whichever option you would like. All right. So let me make a note here. Okay. If I were to compute df dx, I'm going to hold y as a constant. Okay, and if I were to compute df dy, now y is the variable. I'm going to hold x as a constant. All right, let's go ahead and do some examples. Okay, the first example says compute the first partial derivative of the given function, and I have a polynomial of two variables. So let's go ahead and compute the first with respect to x. Okay, so x is the variable, y is a constant. Okay, so polynomial, we know how to compute those. So this becomes 2x, no problem here. Now this next term has a y. It is a constant. You can kind of put them together with the actual constant 3. So then the derivative of this with respect to x would be just negative 3y. Okay. Next term is 2y squared. Remember, this is a constant, right? So the derivative of this with respect to x is 0. Okay. Negative 4x, the derivative is negative 4. Here you can think about this whole term as a constant. So plus another 0. So we can clean this up a little bit. So the answer is 2x minus 3y minus 4. Okay, so that is our first example, computing a partial derivative or the partial derivative of the function with respect to x. Okay, let's do the similar computation for f sub y. Now x is going to be held as a constant. Okay, So x squared with respect to y, that's 0. Okay. Minus, let's see what's going on with the second term. So 3xy, x is a constant, so this becomes 3x. Okay. Plus 2y squared. Now this is a function, so this becomes 4y. Negative 4x, that's 0. Plus 5y, the derivative here is 5, and then another 0. Let's clean this up. So this will be negative 3x plus 4y plus 5. Okay, so this is my first derivative with respect to x, first derivative with respect to y. Okay, so if you've done this before, this will be familiar. Otherwise, if you haven't seen anything of this sort, it might take you some time to get used to the whole idea that one of the variables now is constant. Okay, let's take a look at the next example. Here I'm going to be working with sine of a polynomial of two variables. Okay, let's go ahead and solve this problem. So I'm going to kind of implement the other notation as well. So df dx, or if you'd like to use a more simple notation, f sub x. Okay, so first derivative with respect to x. Okay, how do we do this? Well, first we're gonna do the chain rule, right? Okay, so the derivative of sine is cosine, and we're gonna rewrite the argument. Okay, that doesn't change. So derivative of sine is cosine, good to go, times the derivative of the argument with respect to x. Okay, so I'm making a note here that whatever is inside, I'm going to differentiate it with respect to x. Okay, all right, so cosine, just rewrite that. And now times the partial with respect to x. What do we get here? Y is a constant. So this becomes 2xy, and then minus 2. And of course, the derivative of 4 is 0. So that's our answer here. 2xy minus 2 times cosine of x squared y minus 2x plus 4. If you'd like to rewrite it in a different order, that's fine. But that is the first derivative, first partial with respect to x. Okay, let's do df dy, or f sub y. Okay, first step is exactly the same, right? So it's cosine x squared y minus 2x plus 4 times partial of the argument with respect to y. Okay, and you can see what's going to happen here. This is 0, right? So is this. Okay, once we differentiate it with respect to y. X squared is constant, y is the variable. So what we're going to get is y, sorry, not y, x squared, okay, y is gone, times cosine of this expression. Okay, so these are our two first partial derivatives. Okay, all right, do we have another problem? Yes, tangent. Okay, so let's take a look at this example here, very similar. All right, partial with respect to x. Okay, the derivative of tangent, that's secant squared. I'm going to rewrite my argument, just copy that whole expression inside the parentheses. All right, times the derivative of the argument with respect to x. So that's our partial with respect to x. X cubed minus 3x squared y squared plus 2y to the fourth. Okay, and I'm gonna write that partial of the argument up front. Okay, so over here, what is this going to be? So this is going to be 3x squared. Okay, now y is the constant, x is the variable, so this becomes negative 6x y squared, and then this term is 0, right? So now my answer for this portion would be 3x squared minus 6xy squared times secant squared of this expression. Okay? And that's it. That's as far as we can go. There is no way to simplify anything here. So now let's do df dy. So partial of our function with respect to y. The first step is the same, right? So secant squared x cubed minus 3x squared y squared plus 2y to the fourth times the derivative of the argument with respect to y. So partial with respect to y of the same expression. Okay, so what's going to happen here? All right, so this is going to be 0, but the rest is not going to be 0, right? So if we do this, this is going to be what? Negative 6x squared y, right? Okay, the power rule, we're differentiating with respect to y. X is a constant. And then over here, this is 8y cubed. Okay, so then the final answer, I'm going to put this polynomial up front, rearrange the terms a little bit. 8y cubed minus 6x squared y, okay, times secant squared of this expression. Okay. All right, so that is how we compute partial derivatives. I believe I have one more problem to discuss. Okay, yes, let's go ahead and take a look at this one here. We have a product of two functions, right? E to the negative 2x times cosine of 3x plus y squared. Okay, so let's go ahead and do this problem. So df dx or f sub x. Okay. All right, we're going to do this by applying the product rule, right? So let me make a note here. Product rule. So this would be e to the power negative 2x prime, I'm going to make a note here with respect to x, times cosine of 3x plus y squared plus e to the power negative 2x times the derivative of cosine of 3x plus y squared with respect to x. So this is partial, right? Okay, let's see. What do we get here? This will be negative 2e to the negative 2x times cosine of 3x plus y squared plus e to the power negative 2x. And now we're differentiating cosine, so the derivative of cosine is negative sine. We rewrite the argument times the derivative of the inside with respect to x, and that's 3. Okay, recall that y squared, that would be a constant, so 3x plus y squared prime with respect to x is just 3. Okay, let's see. I can clean this up a little bit, so I could factor out negative e to the negative 2x. And what do I get inside? So this is going to be 2 cosine of 3x plus y squared plus 3 sine of 3x plus y squared. Okay, so that's our first partial with respect to x. And then what about with respect to y? So let's take a look at that. So f sub y. Now e to the negative 2x. It is a function of x. If x is constant, x is fixed, that means this is just a constant, right? So we do not need to apply product rule for this portion because e to the negative 2x acts like a constant. Okay, so this becomes e to the negative 2x times cosine of 3x plus y squared prime with respect to y. All right, so the derivative of cosine is a negative sine, so I'm going to go ahead and pull that negative up here. So negative e to the negative 2x times sine of this argument. Okay, and what about the derivative of 3x plus y squared with respect to y? Now x is a constant, y is the variable, this is 2y. Okay, so we can we can write the final answer as negative 2y e to the power negative 2x times sine of 3x plus y squared. Okay, so this is how you would solve, this is how you would compute partial derivatives of functions with respect to x and with respect to y. Now I'm going to go ahead and stop right here, and there is a second portion of this lecture, and in the second part we're going to talk about second partial derivative and also evaluating partial derivatives at specific values.